So this video provides an example of using EES to simulate a relatively complicated thermodynamic cycle. This one is sufficiently complicated that it requires that we're careful in how we attack the problem and that we use some of the strategies that were discussed in the Using EES Effectively video. This example will use several features of EES that are only available in the professional version, and these include things like equation window tabs and the component library. The eventual cycle simulation that we end up with will be used to illustrate features of the diagram window in the diagram window course, and it will be used in other videos as well to show how we can do optimization. The video is a little bit longer than most, but hopefully it'll be worth your time. So this is a schematic of the partial cooling supercritical carbon dioxide cycle. It consists of 3 compressors, a turbine, 2 recuperative heat exchangers, 2 coolers, a heater, and a couple of T's. So it's pretty complicated, and it's complicated enough that it's interesting. And in this video we'll go through the process of developing a simulation of the cycle so that we can predict its efficiency. So this table indicates the specified operating conditions. So the cycle receives heat from a high temperature reservoir at 650 degrees Celsius, and it rejects heat to ambient down here at 35 degrees Celsius. The high pressure in the cycle, which is the discharge pressure of the main compressor and the recompressor, is 25 megapascals. The pressure ratio of all the compressors is 2, so this is the ratio of the discharge pressure to the suction pressure. You should note that the pressure ratio across the main compressor and the recompressor have to be the same, since they share a discharge and a suction pressure. So I'm only going to define one pressure ratio, the main compressor ratio, pressure ratio for those two. And then finally, the fraction of the flow diverted through the recompressor is 0.4, or 40%. So I'm going to enter each of these operating conditions in a tab of the equations window that I'm going to rename operating conditions, as shown here. And this helps me organize my file. Also, if I want to look at some alternative operating condition, all I have to do is make a new tab called alternative operating condition, and I can easily swap those operating conditions into my model and then back out. So this really makes it easy to organize and run your simulation when you get done. So I'm going to convert all of these inputs to base SI units. Note that the fluid has to be carbon dioxide because I want the real fluid properties of carbon dioxide. So I'll use the written out fluid carbon dioxide here, and I'm going to assign it to a string just to make it easy in case I ever want to look at alternative working fluids in the cycle. So this table lists the component performance parameters that we're going to use to simulate the cycle. So we're going to model all the turbo machines with isentropic efficiencies. We're going to model the heater and the coolers using an approach temperature difference, and the 2 recuperators are going to be modeled using an effectiveness. We're going to assume that there is no pressure drop in any of the heat exchangers of the plumbing, and therefore the pressure is only going to change in the cycle as the fluid flows through one of the different turbo machines. So these component performance parameters are entered into another tab, and I'm going to call that components performance parameters. And again, this makes it pretty easy to organize my file, and if I want to use an alternative set of performance parameters, it's only necessary to define a new tab with those performance parameters. So I'm going to do the simulation itself in the main equations tab. So if I want to access variables from some other tabs in this tab, I need to use the $InsertTab Directive. So I'll put that right at the top here, and I'll have a $InsertTab Directive for the component performance parameters and another one for the operating conditions. And again, if I ever want to try different operating conditions, I would just change the tab that I insert here. I'm also going to put a $Unit System Directive up here to specify the unit system that I'll be using with my thermodynamic function calls. So because we're only going to calculate the efficiency of the cycle, I only need to do the cycle on a per unit of reference mass flow basis. If I want to ever have the system produce a certain amount of power, then all I have to do is scale up the reference mass flow rate until I get to a certain power production rate. So I'm going to select the mass flow rate passing through the turbine to be my reference mass flow rate, and I'll set that equal to 1 kilogram per second. Alright, we can immediately set the pressure at every state point. So the pressures at states 8, 9, 10, 11, and 12 and also 1 must all be the high pressure, so I'll set those. And then the pressure at state 6 and 7 must be the high pressure divided by the main compressor pressure ratio, so I'll set those two. And then finally, the pressure at states 2, 3, 4, and 5 must be the discharge pressure of the precompressor divided by the precompressor pressure ratio. So those are easy to set as well. So I have one property now, pressure, at every single state point. So at this point, I need to pause and think a little bit about how I'm going to tackle this problem. So cycle problems of any complexity are going to ultimately be iterative. And EES is good at that. It can solve large sets of coupled nonlinear equations. But it's going to converge successfully most readily if we're thoughtful about how we enter these equations and how we solve these equations. So I'm going to start by thinking about the states that I know that don't require any iteration. So state 1, which is the CO2 leaving the heater, is set by its pressure and its temperature, which I know is the hot temperature less the approach temperature difference of the heater. So I can get all the other properties knowing this pressure and temperature. I'm going to simplify my life here a little bit by using the RealThermoProps procedure, which will return all of the thermodynamic properties versus a whole bunch of calls to different thermodynamic functions. So there's a few ways to access the RealThermoProps procedure. Here I'm going to use the substance information dialog. So I'll select real fluids and then carbon dioxide. And then over here, I see the available properties list for carbon dioxide, and I'm going to select RealThermoProps. And then down here, I can specify in these drop-down menus that I know the temperature and pressure. And finally, I'm going to append the index square bracket 1 square bracket to each of the inputs and outputs. And I'll select paste, and then here's my call to RealThermoProps. If I don't want some of these properties that it returns, I can just remove them from the output list. But I have to be careful to keep them in the right position, right? So I'll have a blank spot between commas for the properties that I've removed. So here I want entropy, specific volume, and enthalpy. In a similar way, I can specify states 5 and 7. So I'm going to go ahead and do that right away. Again, this is just a couple calls to the RealThermoProps procedure. And at this point, I have not required EES to iteratively solve any set of equations, right? So I can solve after every one of these equations that I am entering, and I can make sure that the units check and everything makes sense. If I go look in the residuals window, I can see that all of my equations so far have been placed in block 0, which is the single equation, single unknown block, right? So very reliable program. I'm not going to encounter any convergence issues with this program. And in that sort of mindset, I'm going to see how long I can keep doing that. So what I'm going to do now is try to work my way downstream from these known states for as far as I can. So starting at state 1 here, I see that the fluid next passes through the turbine. And the turbine has a known isentropic efficiency, and it has a known exit pressure. So this should be sufficient to determine state 2 without iteration, provided that I have a suitable turbine model. So to simulate the turbine and other components, I'm going to use models that can be found in the component library. The component library is not loaded by default, so what I'm going to need to do is load it for this program, and that can be done by adding the $load component library directive to the top of the main equations tab. So then I'm going to navigate through the models in the component library by selecting function info from the options menu, and then click on the component library radio button here. So I'm looking for turbine models, so I'll select turbines from the drop down menu, and then I'm going to scroll through these various models, and it looks like the second one, so turbine 2 _ CL is appropriate, right? I can provide this with the inlet state. So the inlet state here I'm going to provide with the enthalpy and the pressure. I'm going to provide it the outlet pressure, the mass flow rate, the fluid, and then I can either provide it with the isentropic efficiency, which is what would be interpreted if I provided a positive value here for the efficiency, or the polytropic efficiency, which is what it would be interpreted as if I used a negative value here. And the procedure is going to provide as outputs the enthalpy, power, and the isentropic efficiency. So if I need any clarification of how this model works and what it assumes and stuff like that, I'm going to select the info button here to bring up the help page. If I want to use this procedure, I'm just going to use the paste button here, and it'll put it right into my equations tab, and I'll adjust the argument list as needed. So here the input state is indexed as 1 and the output state is 2. Returning the isentropic efficiency is really only valuable if I'm providing the polytropic efficiency, which I'm not, so I'm going to remove that from the list. And at this point I should be able to solve, and when I solve I should see the enthalpy at state 2 has been predicted. So the enthalpy and pressure at state 2 allow me to get all the other properties of interest at state 2, and again I can use the RealThermoProps to do that on one line. If I try to move from state 2 to state 3, I can't really do that at this point because I don't know the conditions at state 10, so I can't really model this high temperature recuperator yet. So I'm going to stop there at state 2 and move on to state 5, which is another state that I know. So if I want to move downstream of state 5, so moving from state 5 to 6, that requires passing through the pre-compressor. I know the outlet pressure of this compressor, I know its isentropic efficiency, so again I should be able to simulate this compressor without iteration. So it's the same kind of thing here. I'm going to go to the component library. I'm going to look through the different models that I have available for compressor. I also select here the appropriate one, paste it into the main tab of the equations window, and then spend a little time modifying the argument list. And once I see that that works okay, I'll go ahead and use the enthalpy that it predicts together with the pressure at state 6 to get all of the other properties at state 6. If I want to move from state 6 through the recompressor here to state 12, that's also possible, right? I know the exit pressure of the recompressor, I know its efficiency, so this is essentially the same process. So I'm going to go ahead and paste the same call in here and modify the argument list. I have to be a little bit careful now because the mass flow rate going through the recompressor is different than the mass flow rate, the reference mass flow rate. So I'll have to make sure I do that correctly. But this should then predict the enthalpy at state 12, and the enthalpy and pressure together should let me get all the other properties at state 12. I can go over here at state 7, which is the other state that I know, and move from 7 to 8. So it's the same kind of process going through a compressor. So I'm going to work through that code here, and this should be pretty familiar at this point. When I get all done with this, I should be able to solve, and you should notice again that so far none of these equations require iteration. So I can enter these equations one at a time, I can solve them, and I can set the units, and if there are any issues, they're very easy to debug because they must be associated with whatever equation I just added, right? And I want to do that as long as possible. But I think as long as possible is now, because at this point I can't move any further downstream from any of the states that I know, and this is where things get a little bit interesting, and I need to come up with a strategy that makes the inevitable iteration easy. So there's probably different ways to do this, but what I'm after here is a way to guess one parameter, and then based on that guess I need to be able to solve the entire rest of the cycle, which would then lead to a single error value that will tell me how far off my guess is, right? As long as I've done that, then the iteration becomes pretty straightforward, and I can ask EES to do that required iteration automatically. But this approach does two things for me. First of all, I can enter the equations one at a time, so again that makes debugging easily, and second, I can start the iteration process from a very good set of guess values, which makes converging easy. Alright, so if I examine this cycle, it looks like I can guess the temperature here at state 3 between the recuperators. So at that point, I should be able to specify states 3 and 8, and those are the two input streams to the low temperature recuperator. So if I simulate the recuperator, I should be able to obtain the states of the outlet streams, so 9 and 4. If I know state 9 and 12, I can do an energy balance on the mixer to get state 10, which is entering the high temperature recuperator. So now I know states 10 and 2, which are the two streams entering the high temperature recuperator. So if I simulate that high temperature recuperator, I should be able to get the states of the outlet streams, which are 11 and 3. And of course, the error then is the degree to which the guessed temperature at state 3 disagrees with the temperature at state 3 coming out of this high temperature recuperator after I solve that recuperator problem. So let's put this approach into action. So first I'm going to guess the temperature at state 3. It doesn't really matter too much, hopefully, how good your guess is. You want to make it somewhat reasonable. So a reasonable guess here is somewhere between the temperatures at state 2 and state 8. So I'm just going to use their average value, and I want to highlight this equation to make it clear that it's just a guess, and it better end up being removed from my equation set or my answer is not right. All right, knowing the temperature and pressure at state 3 allows me to get all of the other thermodynamic properties at that state. So now I need to solve this low temperature recuperator problem. I need to identify the appropriate model to do that. So again, I'll go back to the component library, and now I'm going to select heat exchangers, and I'm going to scroll through the counterflow options. So the model heat exchanger 2_CL looks okay, but if I inspect the help a little bit more closely, I'm going to see that this model requires that the pinch point occurs at either the hot end or the cold end of the heat exchanger. And that may not happen for supercritical carbon dioxide cycles where the specific heat capacity is a pretty strong function of temperature. So if I keep scrolling, I'm going to find heat exchanger 5_CL, and this is probably a better choice as it can deal with the situation where the pinch point occurs internally, because what it's doing is actually dividing the heat exchanger into many sub-heat exchangers. This is a much more computationally intensive model, so I should only use it if I need it. And once we're done, we might decide later to swap in the other option and see if the results change. But for now, I'm going to use heat exchanger 5CL. So I'll paste that into the program. Again, I have to go through and adjust the argument list, and I'll do that here. This N is the number of sub-heat exchangers. If I don't specify it, which I'm not going to, then the default value of 10 is going to be used. This might be something I also want to investigate when I have my model working to make sure 10 is enough. The procedure returns the enthalpy leaving at states 4 and 9, as well as the conductance required for the heat exchanger to achieve this effectiveness and the approach temperature difference. So knowing the enthalpy and the pressure at states 4 and 9 allows me to get the remaining thermodynamic properties. Again, because of how I'm doing this, I can solve these equations one at a time. I can set the units, and it's making it very easy for me to debug and write this program taking this approach. All right, next I'm going to do an energy balance on the mixer. So that's pretty easy. I'm going to assume it's adiabatic, and that's going to give me the enthalpy at state 10, and from that and the pressure at state 10 I can get all of the other thermodynamic properties. And then finally, knowing states 10 and 2, I can go ahead and simulate the high temperature recuperator. So again, I'm going to use heat exchanger 5_CL, even though it's a lot less likely that the pinch point will be internal to the high temperature recuperator. But otherwise, the process here is the same. So I'll paste this in. I'm going to go ahead and adjust this argument list carefully. So if I try to solve now, what I'll find is that I've over-constrained my model, and that's because here this heat exchanger model is predicting H3, but earlier I've already calculated H3 based on that temperature that I guessed T3. So this is where I have to sort of close up my equations. So I'm going to use an alternate variable for H3 here. I'll use something like H3 solve. That'll get around this, and now I'll be able to solve. And after I solve, which takes a bit of time, you'll see that the value of H3 solve and the value of H3 that's associated with my guess value of T3 are not the same, which isn't surprising. It just says that I didn't guess the right value of T3. But I do now have a simulation that's running and it works, right? Okay, so what I want to do now is have EES adjust this guessed value of T3 to cause the model to converge. And here converge means that the value of H3 computed by this heat exchanger model here is identical to the value of H3 that's associated with T3, right? So my first step, and this is very important, is you update all the guess values in EES based on their current values. And then my second step is to remove this equation that sets the guess value for T3. And then finally what I need is another equation that specifies that H3 must be equal to H3 solve. So require that my guessed and my solved values be consistent with one another. And we're in a pretty good spot for this to happen. And if I try to solve now, you'll see it takes a while. It takes a while because the heat exchanger models themselves are iterative and complicated. And then that's inside of the iterations that are happening in order to get the entire cycle model to converge. But you see that EES does finally converge to the actual solution. And the reason that this happens is because we've helped control the iteration process. Right? We are now solving a very large set of nonlinear coupled equations, which is hard, but because of how we did it, and by that I mean controlling the iteration process and starting from a good set of guess values, we've made it much easier. Alright, so the last step then is the efficiency. Right? The problem asks for the efficiency of the cycle, so I just need to calculate here the ratio of the net power out to the heat in from the hot reservoir. And yeah, that gives me this efficiency at this point. So I can do all kinds of other stuff with this model, but hopefully this helped you understand sort of the best practice for how to use EES to deal with cycle simulations that are complicated and iterative.